Swayam Prabha. Digital India. Educated India.
Everyone, this is a course on Introduction to Electronics. This particular course is intended for third semester undergraduate students, particularly for electronics, electrical, computer science and instrumentation students. The purpose of this course is to introduce basic electronics to you. Through this course you will be able to uh, learn about uh, how to design and analyze these circuits and basic devices. Okay. um, in early days, the electronic circuits are mostly based on discrete devices, um, but nowadays the circuits are mostly monolithic based. By monolithic I mean the silicon, there are millions of transistors can be accommodated in a single piece of silicon, so that those circuits can perform complex functions or very application specific functions. The heart of these monolithic circuits are made of usually MOSFET, that is metal oxide semiconductor field effect transistor, or bipolar junction transistor, that is BJT. Apart from those, there are resistors, capacitors, diode and so on and so forth. Okay, so in this particular course we will learn about those devices. Okay, for example, diode, MOSFET, BJT, some building blocks, for example op amp, and also basic digital electronic circuits. So this will create a foundation for you, so that you can later on attend, when you will attend analog circuits and digital electronics courses, this knowledge will be very useful. Okay, so let me go to the next slide. So these are the reference books I will follow. Mostly I will follow Niemann's book, Donald Niemann's Electronic Circuit Analysis and Design. But there are other very useful books. For example, book written by Cedra Smith, that's Microelectronic Circuits. There are books on Millman Halkias, um, book written by Malvino, the very important book, Fundamentals of Microelectronics, written by Rajhavi. So you feel free to use any basic electronics or introduction to electronics book. The syllabus of this subject is tentatively like this. We will talk about basic electronics. I will introduce the roadmap of electronics to you. Then we will move to semiconductor material. Then we talk about PN junction diode, different diode models, and I will briefly then I will talk about applications of diode, mainly half wave, full wave and bridge rectifier application. Then there will be application on regulation, voltage regulation, filter, clipper, clamper, and at the end multi-diode circuit. So after the diode chapter, we will move to discuss BJT, that is basically bipolar junction transistor. This is a very important device as far as the integrated circuit is concerned. We will understand the analysis, understand the basic operation of BJT. We will discuss DC circuit analysis, okay, particularly common base and common emitter configuration, and then we will move to small signal model of BJT, and how this small signal analysis helps in determining its performance in as far as the BJT amplifier is concerned. Apart from amplification, BJT can also be used as switch. So we will learn about this performance also here. Okay. Then we will move to discuss about MOSFET. MOSFET is metal oxide semiconductor field effect transistor. We will discuss basic structure of MOSFET and its operation. We will see the DC circuit analysis, particularly common source circuit, and with and without resistor. Okay. Then we will move to, as we have done in case of BJT, we will move to MOSFET and performance as an amplifier. Okay, we will learn about Q point, load line, etc. We will go through small signal equivalent circuit, and then we will see the performance of common source amplifier. So after discussion about BJT and MOSFET, then we will move to a very important building block, which is op-amp. With op-amp, we will learn different applications. For example, inverting, non-inverting amplifier, buffer, differential amplifier, integrator, differentiator, and so on and so forth. So these are the analog electronics part. Then we will move to digital electronics. We will talk about number system. We will talk about digital gates and symbol. We will talk about truth table and sum of product of sum. So we basically go through Carnot map and how an expression can be reduced through Carnot map. And then later on we will they go through different kinds of flip-flop, for example RSDT flip-flop, etc. So this is tentatively the syllabus of this particular course. Okay, so let's start today's discussion. Electronics is basically motion of charges in a medium. This can be gas, this can be vacuum, this can be semiconductor. Okay, we have probably you have come across these terms that microelectronics and nanoelectronics. Microelectronics, it basically refers to integrated circuit technology, which can produce millions of transistors on a single piece of silicon, as I mentioned to you before, and the dimension of individual devices of the order of even few microns, okay, or even sub-micron level. What about nanoelectronics? Nanoelectronics is mostly it refers to the use of nanotechnology on fabricating electronic components. There is no hard and fast rule about the dimension of nanoelectronics, but say let's say that it's the dimension of the device less than 100 nanometer is we can call them as nanoelectronic devices. Okay, in fact today's microelectronics, these are the MOSFETs, is in the nano regime, because we are making devices which get length of around 22 nanometer, 10 nanometer even today. Okay, so they are very tiny. That is why we are able to accommodate millions of transistors on a very small single silicon die. Okay, apart from silicon, in nanoelectronics we use other materials. Those are non-silicon materials, for example, and we fabricate different structures. For example, we fabricate nanotube, we fabricate nanopillars, nanowires, nanoparticle, and so on. And they have different applications, very important applications. So which basically helps silicon based circuits as well. Okay, now if we talk about bit of a history, I am tempted to put three important milestones for electronics. The first milestone I want to mention is vacuum tube, mostly driven by Thomas Alva Edison. There are vacuum tubes in the form of diode, triode. Particularly these was used during World War I and World War II to develop many circuits. Okay, so this is the picture on the right hand side is about a triode, vacuum triode. Then the people managed to discover transistor around 1947. It was John Bardeen, Walter Brettin, and William Shockley from Bell Lab. They managed to fabricate and develop a very important device known as bipolar junction transistor. We will learn about bipolar junction transistor in this course. And then from there, Jack Kilby and Robert Noyce around 1957-58 developed integrated circuit. And as I mentioned to you before, integrated circuit or IC is basically where we use millions of transistors on a single silicon die. For example, this is an image or a layout. Rather, this is a layout of an electronic circuit, and this is fabricated from a commercial foundry on a single piece of silicon that you see in the right hand side. This for example, these chips are very tiny. This is this particular chip of the order of 5 millimeter by 5 millimeter. So after fabricating, what we do, we dice the wafer and we have individual chips. So we can put the chip in a package. So this is a package, and the chips contain pads. You see these are pads which are basically the access points of the circuits which are present inside the chip, and we can then bond these pads with these connections present in the package, and use this to access circuits which is present inside. Anyway, so these are the three milestones I thought I just mentioned to you, and this integrated circuit basically create a revolution, and whatever integrate electronic gadgets we see today is built on this integrated circuit, which as I mentioned to you before, can perform many complex operations. Another important aspect I would like to mention, this is Gordon Moore of Intel, co-founder of Intel. There is a famous law known as Moore's law. It's basically a visionary statement. Moore around 1960-65 realized that the electronics industry is moving in a direction where the number of transistors incorporated in a single piece of silicon approximately double in every 24 months. Okay, this was a prediction, and later on most of the blue chip companies, semiconductor companies, try to follow that. On the right hand side you see transistor number per chip, and you see the transistor number increases from 10 to the power 3 to 10 to the power 4, the 10 to the power 7, 10 to the power 8 on the same area of a silicon, and they have plotted these against versus year. Okay, so you see all these processors which are packed with millions of transistors on the single silicon. Okay, so that way we managed to improve the speed of the circuits. We managed to improve functionality of the from the circuits, and this has been from then on, this has been a revolution. And you have we have today all our electronic gadgets very compact, and they are power efficient, they are very fast, and so on and so forth. And all this is possible because of this revolution in integrated circuits. Okay, now let's talk about electronic signals. Electronic signals are there. Mainly two kinds of electronic signal. One is the analog signal, and the other is digital signal. Most of our signal which we see in the nature is analog signal. Signal level may have a any value in case of analog signal. Okay, so all the real world signal, as I said, is analog signal and can have infinite amount of signal resolution, and there will be noise and distortion and so on and so forth. What about digital signal? We tend to convert analog signal into digital signal, so that many of the operation can be done more efficiently. Particularly the digital signal is more immune to noise. Usually digital signal contains logic levels, for example logic 1, logic 0, and so on and so forth. So these signals are easier to handle and mostly immune to noise, contrary to analog signal. However, there are errors present in the digital signal in the form of quantization error. Okay, so we'll learn more on this when we talk about digital circuits. Now, if we just briefly cover electronic material and electronic devices, particularly material we use for electronic devices, we use um, um, semiconductor material, particularly silicon. There are other materials, for example gallium arsenide, which we use to fabricate an electronic device. Okay, now this let me yeah so to so electronic device, and we fabricated using semiconductor material. Okay, primarily silicon, but there are other materials, as I mentioned. In the gallium arsenide is one of the is also one of the popular material, particularly for high speed circuits. And the other key components in any electronic device are insulator. Okay, for example we use SiO2, and also silicon nitride, while fabricating electronic devices from foundry. And we also use metals, for example aluminium. We use nowadays we are using copper as well. And sometime if we need a high temperature application, we use metal like tungsten. Okay, as far as the semiconductor devices are concerned, and we will discuss diode, PN junction diode. We will discuss in this course bipolar junction transistor. We will discuss metal oxide field effect transistor, and so on and so forth. Okay. Now, if we look at the periodic table, silicon is basically group 4 element. Okay, silicon is basically group 4 element. So it has 4 electrons at the outermost shell. The table also contains, you see, phosphorus, which is group 5 element. Okay, phosphorus and arsenic, and there is boron, aluminium, gallium, and so on. So boron, they are sitting in the group 3 of the periodic table. Okay, as silicon is sitting in the group 4 position. So as I said, it has 4 electrons at the outermost shell. It basically interact with neighboring 4 silicon atoms to form covalent bonds. Okay, so here is the image. So each silicon here, so it will interact with 4 adjacent silicon atom. Okay, and form covalent bond, so that it can effectively have 8 electrons at outermost shell. Okay, now when temperature goes up, electrons in the covalent bond can become free. Of course, that depends on the value of the temperature or the energy. If we in case of silicon, the band gap, we know, you probably know, is around 1.1 electron volt. That is the distance, that is the energy gap between the conduction band and the valence band. And if these electrons which are present in the valence band manage to go to conduction band, then they are free to move. Okay, so they are free to move in the conduction band. Similarly, it will create a vacancy here, which we call it holes. Okay, let's go to the next slide and see this aspect. So this free electrons occur because of the breaking of this covalent bond. For example, I have shown here there is a breaking of covalent bond, and so this electron will basically move in the this electron will reach from covalence band to conduction band, and they are free to move, and they will create a vacancy in the valence band. So this will basically create an electron hole pair. Okay, electron is free to move in the conduction band, while these holes which will move to the valence band, in effect basically electrons as well is moving to the valence band, because you see, as electrons are neighboring electrons jump into this vacancy, the holes will move in the opposite direction of the movement of the electron. Okay, but the usual concept is this charge carrier we consider as a positive charge carrier, and the particle and the corresponding particle as holes which is present in the valence band, whereas electrons we consider a negative charge carrier, and they are sitting in the conduction band. So electrons in the conduction bands are free to move, holes in the valence band are free to move. Okay, now so the motion of holes effectively in the opposite direction as motion of electrons. Okay, so it should be electrons, so opposite to that of the motion of electrons. Okay, now let's talk about electron density with temperature. Electron density is usually represents by Ni. So that's basically intrinsic carrier concentration. This is basically represents by Ni b t to the power 3 by 2 exponential minus Eg by 2 kt, where b is related to specific semiconductor material. In case of silicon, it's around 5.23 into 10 to the power 15, and we can use these to find out the carrier concentration in the semiconductor. And of course, as you see, carrier concentration depends on temperature, because I mentioned that with increase in temperature, these covalent bonds will break, and then the electrons go from valence band to conduction band, and then they are free to move. So this electron moves from here to here and so on. Okay, so these free carriers also known as intrinsic carrier. Okay, and we can find intrinsic carrier concentration. In case of silicon, intrinsic carrier concentration typically of the order of 10 to the power 10, precisely it's around 1.5 into 10 to the power 10 electrons per centimeter cube at room temperature. This at room temperature is very important, because if you increase temperature, you see in this formula the carrier concentration, intrinsic carrier concentration will increase. Okay, so however, the point I would like to make, this electron or hole concentration, because this will create electron hole pairs, this the thermal energy or any other form of energy. In case of intrinsic semiconductor, they will create an intrinsic carriers like electron or holes. So these pairs are for appreciable amount of current. This is not enough, because you see the order is around 10 to the power 10, and that is very low. Okay, however, this breaking of bond depends on breaking of covalent bond depends on how much energy we are providing, because the electron needs to go from valence band to conduction band, so they needs at least the energy of the order of Eg, that is the band gap of the semiconductor. Okay, and as I said, there is an exponential relationship between this free electron density and this band gap energy. Okay, so this is This is that relationship. Now, let's talk about, I should have mentioned about this intrinsic and extrinsic semiconductor. So semiconductor are mainly two types, intrinsic semiconductor and extrinsic semiconductor. Okay, in case of the intrinsic semiconductor is the basic semiconductor where we don't have or we don't incorporate any impurity. Okay, so the in case of intrinsic semiconductor, the carrier concentration Ni is for example in case of silicon is around of the order of 10 to the power 10 per centimeter cube at room temperature. What about extrinsic semiconductor? If we manage to incorporate impurity in the semiconductor, that will be extrinsic semiconductor. For example, we can incorporate impurities in the form of phosphorus, in the form of boron. Okay, phosphorus is a group 5 element that we will discuss in the next slide. Okay, let's go through the intrinsic semiconductor first, then we will discuss the extrinsic semiconductor. So in case of intrinsic semiconductor, as I mentioned to you before, it doesn't have no other impurities. Okay, and density of electrons or holes are the same, and that is usually represents as Ni. Okay, and these in the electron hole pair will be created when because of the breaking of covalent bonds. Okay, and with increase in temperature, electron hole concentration will increase. Okay, and this conductivity of silicon increases. Now this usually this is represents as an Np is equal to Ni square, where N is the concentration of electrons and P is the concentration of holes. Okay, and product of this is equal to Ni square. So the carriers these carriers can randomly move, and some electron from conduction band may jump back to the valence band and recombine with holes. Okay, this particular phenomena is known as recombination. So let me repeat it once more. So if there is a breaking of covalent bonds, the electron from valence band will go to the conduction band. Okay, and they are free to move. Now it might happen that those electrons jump back from conduction band to valence band and meet with holes. So this particular process is known as recombination. And usually recombination, of course, that depends on a number of free electrons and holes present. Okay, so the more the number of electrons and the free electrons in the conduction band, there will be more chances that they will recombine. Of course, that depends on number of holes present in the valence band, but the number of holes and electrons in the number is in the same in case of intrinsic semiconductor. Okay, and so in thermal equilibrium, this recombination rate and the generation rate of the electron hole pair, they are basically same. But as I mentioned to you in the last slide, carrier concentration depends on temperature. Okay, so that is not very good news because this carrier concentration, if you increase temperature, if it increases, then what will happen? The devices, if you take to a place where the temperature is much higher, then you will have more current. So depending of temperature is not good. And also another point I have mentioned before is the carrier concentration is not enough. In case of intrinsic semiconductor, because it is only around 10 to the power 10 per centimeter cube at room temperature in case of silicon. Okay, let's move to extrinsic semiconductor. Extrinsic semiconductor is basically impure semiconductor. This is usually achieved through doping. Okay, so use a process known as diffusion or ion implantation to dope a semiconductor. Now this will substitute semiconductor atoms. Say if I am doping silicon, it will substitute usually substitute silicon atom and occupy those sites, although it can also occupy interstitials. Let's not go into that direction. but depending on which dopant you are incorporating, they might occupy actual crystal sites, or they might occupy lattice sites, or they might occupy interstitial. Anyway, so let's just stick to the substitution case. So this will substitute semiconducting atoms. For example, if we talk about silicon, they will substitute silicon and these impurity atoms, and they will occupy the lattice sites. Now it is found that these impurity atoms, they can form energy states which is very close to that of conduction band or valence band, depending on what kind of dopant we are using. And those dopants can provide extra electron or provide extra holes. So in the usual impurities we use for extrinsic semiconductor are group 5 elements, for example phosphorus or arsenic, and we call these extrinsic semiconductor as n-type semiconductor. Okay, so if we dope silicon with phosphorus or arsenic, we call it n-type semiconductor. If we dope or if we incorporate boron in silicon, boron is a group 3 element. Okay, so so that then becomes p-type. So we will have we have basically n-type semiconductor, okay, where predominantly there will be electrons, okay, as a charge carrier, and if we dope with boron, that is group 3 element, the charge carrier is predominantly holes. Okay, so these electrons and holes basically take part in the movements of electrons and holes, basically create current. Okay, now let's mention this a little bit more detail. Okay, so you see here we have doped silicon with phosphorus. Okay, and this doping has changed the electrical property of the material. Okay, for example, if silicon is doped with phosphorus, it becomes n-type. Okay, how it becomes n-type? Let's try to understand it in more detail. Okay, so this is my conduction band. Okay, and this is my valence band. So valence band will have lots of electrons. Okay, packed with electrons. Now what will happen is when we so this is the so if we use some form of energy, these electrons can jump, for example thermal energy, and reach to the conduction band, and they are free to move. So this is the case for intrinsic semiconductor. Now in case of extrinsic semiconductor, for example if we talk about n-type semiconductor, which can be achieved if we dope silicon with phosphorus or arsenic, it is found that they will form an energy level which is very close to that of conduction band. Okay, so phosphorus atoms are sitting here. Okay, now phosphorus is sitting in the group 5 element of the periodic table, group 5 of the periodic table. So phosphorus contains basically 5 electrons at the outermost shell. So phosphorus, what it will do, it will form covalent bond with 4 neighboring silicon. Okay, it will form covalent bond with 4 neighboring silicon, but 1 extra electron remains, because phosphorus only need 3 electrons, right? So because it has 5 electrons at outermost shell, we all know that we need any atom need 8 electrons at the outermost shell to form octet, okay, or stable configuration. So this additional electron, okay, in case of phosphorus, which is loosely bound, and now as phosphorus atoms are sitting in this particular energy level, which is very close to that of the conduction band. Now with very little amount of energy, phosphorus will be ionized, and this electron which is free, which is sort of free, can go to the conduction band. So you see, with very little amount of energy, the electrons from this energy level can be donated to the conduction band. In fact, these phosphorus atoms are known as donor. Okay, phosphorus atoms are known as donor because they donate the electron very easily to the conduction band. So one important point in case of n-type semiconductor is that is also true for p-type semiconductor, but let's only talk about n-type semiconductor. Here we will have lots of electrons in the conduction band, but there will be no holes in the valence band, or very little amount of holes, depending on if some electrons manage to cross this energy barrier and reach this reach the conduction band. Okay, so there will be a little number of holes, but mostly the carrier concentration is made of electrons. So phosphorus is donating electrons, and phosphorus in this case known as donor. Okay, we usually represents the concentration of phosphorus as Nd. Okay, Nd, D stands for donor. Okay, so Nd is the concentration of the phosphorus present in the silicon. Of course, that doping that is basically the doping concentration, and we usually consider that most of the dopants will be ionized. So phosphorus will sit here as positive ions. Okay, positive immobile ions, while they will release the electrons to the conduction band with little amount of energy. Okay, the same argument is true for when you dope silicon with boron. Okay, so boron is sitting in the group 3 in the periodic table. So that means boron has 3 outermost electrons. So what boron will do, it will form covalent bonds with 4 silicon, but it will need 5 electrons to form octet. To complete the octet. So what will happen is there will be a thing called holes. Okay, so this is known as hole, which is a deficiency of electron, or these holes can be occupied by adjacent electrons, and basically if an electron jump from this covalent bond to these holes, the holes will move to the opposite direction. So the hole movement is opposite to the movement of the direction of electron. Okay, but in case of boron doping, what happens, let me draw that diagram again. So this is my conduction band, and this is my valence band. Now this when you dope with boron, it is found that the energy level is very close to that of the valence band. Okay, boron energy level is very close to that of the valence band in case of semiconductor, in case of silicon. So what happens, these borons which have holes, which is basically giving rise to what they will do, they with little bit amount of, because boron has has only 7 7 outermost electrons. So if you give a little bit of energy, the electrons from valence band will jump and reach to this level. So electrons from valence band will jump and interact with boron. So you will end up with negative immobile ions. Okay, negative immobile ions here, okay, is contrary to phosphorus, which will form positive immobile ions, because phosphorus will donate electron. Here the borons will basically accept electrons from the valence band. Okay, and they are known as acceptor. We usually represents boron concentration as Na. Okay, as Na, and we assume that with minimum of energy, most of the boron will be ionized to negative immobile ions, and there will be plenty of holes, because as electrons move from this from valence band to this to this to the energy level where borons are present. So it will create lots of holes in the valence band, but there is hardly any electron present in the conduction band. So in case of you see, in case of n-type semiconductor, when we dope silicon with phosphorus, we have plenty of electrons in the conduction band, but hardly any holes in the valence band. Okay, so we have plenty of electron in the conduction band, but hardly any holes in the valence band. Similarly, in case of p-type semiconductor, okay, when we dope silicon with boron, um, the mostly the carriers are holes and they are present in the valence band. Okay, but there is hardly any electrons present in the conduction band, because electrons needs to reach an electron to the conduction band, you need to give higher amount of energy so that they can cross this energy gap. So in other words, in case of p-type semiconductor, we will have lots of holes in the valence band, because electron jumps from valence band to this defect state of boron, and they have boron has accepted those electrons, and they are the acceptors. So they have created holes, and this hole concentration is around is close to Na, because we will assume that most of the borons will be ionized. Okay, most of the borons will accept electrons, and they will be ionized, and they will form immobile negative ion. Okay, while leaving holes in the valence band. So the number of holes, or the hole concentration, is same as the concentration of dopant, that is Na. And similarly here, the concentration of the electron in the conduction band is basically the concentration of the phosphorus, or concentration of the dopant, Nd. Okay, now, so you see the point to be noted here, in case of extrinsic semiconductor, in case n-type semiconductor, the majority carriers are electrons. Okay, whereas in case of p-type semiconductor, the majority of carriers are holes. Okay, it is unlike in intrinsic semiconductors, where in case of intrinsic semiconductor, the number of holes and electrons are same, but here for n-type, the majority of carriers are electron, and for p-type, the majority of carriers are holes. Now let's discuss this a little bit more, although I have mentioned this already. In case of extrinsic semiconductor, as I mentioned to you before, electrons will easily reach to covalent to this conduction band, and so these pentavalent impurities basically donate excess electron, and therefore named as donor. Okay, so as I said, allowable energy levels are introduced very close to the distance of the conduction band. So you see this energy level is known as Ed. Okay, donor energy level, and this energy level, which is an energy level associated with acceptor, is known as Ea. Okay, now as I said to you before, in case of n-type semiconductor, majority carrier is electron. Okay, and in case of p-type semiconductor, majority carrier is holes. Okay. Now let's discuss what about the charge density. Okay, the charge density in case of doped semiconductor, of course it depends on dopants. Okay, either it's Nd or Na, depending on which kind of dopant you are using. But in a semiconductor is electrically neutral, obviously. Okay, so magnitude of positive charge density must be equal to the magnitude of the negative charge density, right? So so we can write Nd plus P. Okay, Nd is the positive immobile ions, plus P is equal to Na. Na is the negative immobile ions. You remember the concentration of negative immobile ions plus N. Okay, that is the electron. So this is from charge neutrality we can write, because because you see the semiconductor is the electrically neutral piece of material. Now say if we have like n-type material, then in that case Na will be equal to 0. Okay, Na will be equal to 0, because in case of n-type material we are doping the semiconductor with only phosphorus, only group 5 elements. Okay, so in that case N will be much greater than P. As I mentioned to you before, in case of n-type material the majority of carriers are electron, and there is very little number of holes present in the valence band, because the electrons are coming from the phosphorus itself, okay, from the energy level which is very close to that of the conduction band. So we can write n small n, that is the concentration of electron, nearly equal to Nd, because we are assuming that almost all the phosphorus atoms will be ionized, okay, with very little amount of energy, right? So a point to be noted here, this concentration of N is independent of temperature, because it depends on the number of dopants you are using. Okay, so this is contrary to intrinsic semiconductor, and very important advantage, because in case of intrinsic semiconductor the carrier concentration depends on temperature. So as I said, that is not good, because then if you take your electronic device to a particular place where the temperature is very high, then the amount of current we will get is more, whereas if you go to the place where the temperature is very low, so that there will be change in current, so that is not good. We want the device current should be as less dependent with temperature as possible. So if you dope with silicon or any semiconductor, then the concentration of these free carriers, okay, depends on the dopant concentration, not depends on temperature. So this is a very important advantage if we dope with semiconductor with a dopant. Another advantage of extrinsic semiconductor is that the number of carriers is now much higher compared to that of intrinsic semiconductor, which is in case of silicon around of the order of 10 to the power 10 per centimeter cube. So we can use a much larger amount of dopants and increase the carrier concentration. So that is another advantage. So one advantage is dopant concentration hardly depends on temperature, and second advantage is the number of dopants, number of free carriers will be much higher now, so you can have much larger current with extrinsic semiconductor. Okay, so we need extrinsic semiconductor to develop electronic devices, right? So we can write that expression again. So n multiplied by p suffix n is equal to ni square. Okay, so n is the electron concentration of n-type material, whereas whole concentration of p-type material is Pn. So this suffix represents which type of semiconductor I am using. So this suffix n means n-type semiconductor. If the suffix is p, so in this case the suffix is p, so this is a p-type semiconductor. Okay, so again this relation holds good whether it is intrinsic semiconductor or extrinsic semiconductor, and we can write nn multiplied by pn is equal to ni square. So you see minority carrier concentration Pn can be written as ni square over Nd, because you know all the dopant will be ionized. So Nn nearly equal to Nd, right? Nn nearly equal to Nd. So we can find out Pn, that is minority carrier concentration. In this case, minority carrier is whole, that is Ni square over Nd. And that number of holes is much smaller compared to that of electron. Similarly, in case of p-type semiconductor, we can write Np multiplied by Pp is equal to Ni square, and in that case the concentration of Np is much smaller compared to the majority carrier holes, and the relation is in Ni square over Na. So with this we will basically stop today's lecture. Just to summarize, because in the next class we will start discussing current in semiconductor. Okay, just to summarize whatever we have discussed today, we have discussed the roadmap of semiconductor. We mentioned that in early days we used to use a lot of discrete devices to develop a circuit, electronic circuit, but nowadays most of the electronic circuits are integrated circuits. That means the millions of transistors present in a single silicon die, and that way we managed to improve the performance, the functionality achieved from these circuits improved quite a lot. And we can do complex function. We achieve complex functionality through the from this tiny silicon die. Okay, so nowadays our electronic gadgets are very compact, they are power efficient, they are high speed, and so on and so forth. And all this is possible because of this evolution in integrated circuit. Now this integrated circuit contains different kind of devices, but mostly BJT and MOSFET. We will discuss about those devices in this course. But today we have learned about semiconductor. Semiconductor is in between metal and insulator. In case of the IC design, integrated circuit design and fabrication, we mostly use silicon, but there are other materials which is like a gallium arsenide and so on. So but the silicon is the most popular material. So apart from silicon, we use silicon dioxide. We will see where silicon dioxide is required, but silicon dioxide is insulator. We also use metals, for example aluminium, copper or tungsten, okay, to take contacts from the devices. Okay, now these semiconductor is of two type, intrinsic semiconductor and extrinsic semiconductor. The intrinsic semiconductor contains electron hole pairs, and these the concentration of these carriers mostly depends on temperature, and the concentration level is much smaller. So it's of the order of around 10 to the power 10 per centimeter cube in case of silicon, and that is not good enough to have a large amount of current. So what we do, we dope or incorporate impurity using a process known as diffusion. Also you can use ion implantation to realize extrinsic semiconductor, and such doped semiconductor is very useful to develop electronic devices, because there are two key advantages. One advantage is if you dope semiconductor with then what will happen, the carrier concentration no longer depends on temperature, so that is a major advantage. Another advantage is now the carrier concentration is much larger than that of Ni, that is intrinsic carrier concentration. That way you can increase you can get larger amount of current from this extrinsic semiconductor. Lastly, extrinsic semiconductor is of two type. One is the N-type semiconductor, where the majority of carriers are holes, majority of carriers are electrons, and the P-type semiconductor, which is realized using boron doping, where the majority of carriers are holes and minority of carriers are electrons. So with this I am stopping here today. In the next class, what we will do, we will learn about current present in semiconductor, mostly drift current and diffusion current. Okay, we will learn about their expressions and so on and so forth. So thank you very much for your attention.